Hi, I'm Mark Barsamian. In this video, I'll be discussing relations on a set. More specifically, we'll be talking about the Cartesian product of sets, relations on a set, properties that relations on a set may or may not have, and we'll be talking about what are called equivalence relations. This material is from our book, Millman and Parker's book, Geometry, A Metric Approach with Models, 2nd edition. More specifically, section 1.2, pages 4 to 7. The corresponding homework exercises are here, a big collection of exercises from section 1.2. We'll start with a definition of ordered pair. If A and B are sets, then an ordered pair is a symbol of this form, parentheses little a comma little b, where little a is in set capital A and little b is in set capital B. Two ordered pairs are called equal if their left elements are equal and their right elements are equal. The Cartesian product of A and B is written this way and spoken A cross B, but you have to be careful. When A and B are sets, this thing A cross B is referring to the Cartesian product, as I said. In earlier courses, you had symbols like this in the cases where A and B represent vectors, and that symbol is, spoken A cross B, means something very different. In vectors, that would mean the vector cross product of A and B. In sets, that same symbol means the Cartesian product of A and B, means something completely different. So that's what I refer to as the usage of a symbol. That is, the meaning of this symbol depends on what A and B represent when the symbol is written down. So when A and B are sets, that symbol means this. It means the set, so the set A cross B, is the set of all ordered pairs that have little a on the left, a member of set capital A, and little b on the right, a member of set capital B. Power notation is sometimes used for Cartesian products. The Cartesian product of a set with itself is sometimes denoted using exponent notation. So A cross B would be denoted A superscript 2. So for example, this symbol, R superscript 2, denotes the Cartesian product, R cross R. In this Cartesian product, these symbols, 2, 3, and 3, 2, denote different ordered pairs. This symbol denotes the collection of all ordered pairs. Here are two examples of ordered pairs, and there are different ordered pairs. So in the Cartesian product, order matters. Now compare that to the situation with sets. In set notation, order does not matter. So for instance, the set curly bracket 2, 3 is equal to the set curly bracket 3, 2. So order matters in ordered pairs and in the Cartesian product. Order does not matter when you're talking about sets. Now I want to talk about what are called binary relations on sets. If you say these words, capital R is a binary relation on capital S. What that means is that S is a set and that capital R is a subset of S cross S. Now remember what S cross S is. That's the Cartesian product of S with itself. That's a collection of ordered pairs. So to say that R is a subset of that means that R is a set and what it contains is ordered pairs from S cross S. Now some additional terminology goes with this. If I say these words, little s is related to little t, and that's denoted this way. I put little s tilde little t, or I can put little s and little t as subscripts to the left and right of this symbol capital R, or other symbols can be used. If I say those words or if I write those symbols, what that means is that that ordered pair, little s comma little t, is an element of the relation R. Now to say the words little s is not related to little t is written this way, little s tilde with a slash t. What that means is that that ordered pair, little s comma little t, is not an element of the set that's the relation, capital R. Now it's often helpful to illustrate a binary relation on a set. In general, there can be more than one way to do that. For binary relations on the set of real numbers, the illustration can be in the form of a graph in the R2 plane. Our first example of a relation is the less than relation. So set capital R is defined to be the set of all ordered pairs x comma y such that x is less than y. We could say that this symbol, spoken x is related to y, means x is less than y. Or we could say that this symbol, x tilde y, which is again spoken x is related to y, simply means x is less than y. Now the thing is, these symbols are not really that helpful. If we have such a nice symbol like this, let's just use that symbol to denote the relation. Notice that statements involving relation symbols can be true or false. So for instance, this statement is true, while this statement is false. 2 is less than 5 is a true statement. 5 is less than 2 is a false statement. We could write this, 5 is not less than 2. That would be a true statement. So in words, we'd say that 2 is related to 5. That is, 2 is less than 5. On the other hand, 5 is not related to 2. That is, 5 is not less than 2. Here's the graph of the less than relation. So the shaded region is the collection of all ordered pairs in the xy plane such that x is related to y. So notice that in this diagram, the point 2 comma 5 is in the shaded region. So 2 is related to 5. 2 comma 5 is an element of the set. That's the relation. On the other hand, in this diagram, the point 5 comma 2 is not in this shaded region. So maybe I should put a circle there. So 5 comma 2 is not part of the relation. So we say that 5 comma 2 is not an element of R, whereas 2 comma 5 is an element of R. Go on. Example 4, the less than or equal to relation, defined this way. R is the set of ordered pairs such that x is less than or equal to y. So I can make a graph of this relation as well. Now we have the same points that we talked about in the previous example. 2 comma 5 is an element of this relation, where the point 5 comma 2 is not. But there are some differences between the previous relation and this one. Notice that in this relation, the point 3 comma 3 is an element. 3 comma 3 is in this relation because 3 less than or equal to 3 is true. Let's go up to the previous relation. In this relation, the ordered pair 3 comma 3 is not an element of R. Let's go on. Example 5. We define a relation on the set of real numbers by this equation. We say x is related to y to mean x squared equals y squared. Well, the graph of this relation is very simple. The graph consists of these two lines, the line y equals x and the line y equals minus x. So for instance, some points that are in this relation, 3 comma 3 is an ordered pair that's in this relation because 3 squared equals 3 squared. But 3 comma minus 3 is also in this relation because 3 squared equals minus 3 squared. Similarly, minus 3 comma minus 3 is in the relation, and minus 3, 3. And of course, the point 0, 0 is in the relation. Example 6. Define this relation on the set of real numbers, the set of all ordered pairs such that x squared plus y squared equals 1. Well, the graph of that relation is a circle of radius 1. You can label a bunch of famous ordered pairs that we know are in that relation. Now I want to discuss 3 properties that relations on a set may or may not have. The first is the property of being reflexive. We say that a relation is a reflexive relation on a set to mean this: every element in the set capital S is related to itself. Now we can write that in formal notation, that is abbreviated using logical symbols. Can write it this way. Here's the quantifier. For every element A in set capital S, A is related to A. Every element of S is related to itself. We use these words, R is a symmetric relation on set capital S, to mean this: for every 2 elements, A and B, in set S, if little a is related to B, then little b is related to A. So written formally, we would use the quantifier, the upside down capital A, to denote for all, or for every, A and B in set capital S. If A is related to B, then B is related to A. So notice that the definition of symmetric uses 2 letters, A and B. The definition of reflexive only uses 1 letter. So you don't have to have different letters on the left and right sides of the relation symbol. And you don't have to have 2 letters in the definition of a property. Finally, we use these words, R is a transitive relation on S, to mean this: for every A, B, and C in S, if A is related to B and B is related to C, then A is related to C. Written formally, that is abbreviated using logical symbols, we would write, for all A, B, and C in S, if A is related to B and B is related to C, then A is related to C. So notice here that the definition of transitivity uses 3 letters. Now, only 2 at a time get put to the left and right of the tilde symbol. So A is related to B, that's one use of the relation symbol. B is related to C, that's another use of the relation symbol. And A is related to C. So there are 3 letters involved in the definition, but only 2 of them get used at any one time. Now, we're often interested in determining whether or not a particular relation has any of the 3 properties above. Now, each of those properties is a logical statement. Each may be true or false. If the statement of one of those properties is true for a certain relation, then we say that that given relation has that property. On the other hand, if the statement of one of those properties is false for a certain relation, then we say that the relation does not have that property. If the statement of one of the properties is false, then the negation of that statement will be true. So therefore, it'll be important to understand how to find the negations of each of the statements above. Now, finding the negation of quantified statements may have been discussed in your Math 3050 class or your CS 3000 course, but we should review the concept here just to make sure that you're all fresh with this concept. So here's the formal statement of what it means for a relation to be reflexive. For all A in the set S, A is related to A. To find the negation of this statement, we proceed in stages. We start by just simply parking the word not in front of that. So that would be spoken, it is not true that for all A in set S, A is related to A. Now, that kind of simple way of negating something, well, it's simple, but it's often not helpful. So in other words, what does that really mean? Well, this statement can be made more clear if we move the negation to the right in this expression. So I'm going to do that in stages. I'm going to move the negation one notch to the right past that quantifier. So the not is going to show up out here. Now when it moves past this quantifier, the quantifier gets changed to an existential quantifier. So there we've moved the negation symbol to the right past this universal quantifier and changed it to this symbol, which is spoken, there exists an A in set S such that. That's called the existential quantifier. So now we have moved the negation symbol to the right so that it's now parked in front of what was the original predicate. Now we can clarify this more by dealing with this negation. We can apply this negation to this predicate. And when we do that, it becomes the following. This is spoken, there exists an A in set S such that A is not related to itself. So you see that our original negation had the not out front, and it ends up way over to the right as part of the predicate. So the original sentence was spoken, it's not true that for all A in set S, A is related to A. And then the final kind of simplified version of the negation is this. There exists an element in S such that A is not related to itself. So in most situations, this is clearer. So a clearer statement of the negation is the thing that we finally ended up with, whereas the first statement is sort of the easiest way to build the negation. So I would refer to this as simplifying in a way, clarifying, whatever. I don't think the book uses this kind of terminology, or I don't think your discrete math book used this kind of terminology either. But the idea is we move the negation to the right. Let's go on. Now we want to negate the statement of symmetry. Remember that to say that R is a symmetrical relation on a set S means this. For all A and B in set S, if A is related to B, then B is related to A. Now, when finding the negation of this, we're going to need this fact about the negation of a conditional statement. The negation of a conditional statement is an AND statement. So the negation of if P then Q is P and not Q. So let's form the negation of this statement, the cheapest, easiest way, just by parking the negation in front. And then let's simplify by moving the negation to the right in stages. So in this first step, we've moved the negation past that quantifier, past this universal quantifier, turning it into an existential quantifier. In the second step, we'll negate this if-then statement using this rule. And then finally, we will simplify this. What does it mean to say that not B is related to A? Well, that just simply means that B is not related to A. So I'll just write that more clearly. So this is spoken, there exist elements A and B in set S such that A is related to B and B is not related to A. So that's what it means for a relation to not be symmetric. There exist elements A and B in set S such that A is related to B and B is not related to A. Maybe we should go back and be clear about our result from the previous page. This is what it means for a relation to not be reflexive. Finally, let's consider the negation of the statement of transitivity. Here's the statement of transitivity for all A, B, and C in set S. If A is related to B and B is related to C, then A is related to C. Well, I will go through this in stages. Again, I won't talk, I'll just simply write and get through this more quickly. So there's the statement of a relation being not transitive. There exist elements A, B, C in set S such that A is related to B and B is related to C and A is not related to C. Let's go back and revisit some of our earlier examples. Recall the less than relation. This relation, x is less than y. What properties does this relation have? We have to justify our answers. Well, we have to consider the properties of reflexive, symmetric, and transitive. Now remember that reflexive is this. Every element is related to itself. The negation of that is this. There exists an element that is not related to itself. Well, let's go back up and look at the graph of the less than relation. There's the graph of the less than relation. Now we can see that there does exist an element that's not related to itself. 3, 3 is an ordered pair that is not in our relation. So 3 is a real number that's not related to itself. So we can see that this relation is not reflexive. Now let's go back again and look at the definition of reflexive and then the negation. Remember that the statement of reflexivity is a universal statement, whereas the statement of its negation, to say that something is not reflexive, to say that a relation is not reflexive, is an existential statement. Now we want to prove that the relation is not reflexive, so we want to prove that this existential statement is true. Well, you prove an existential statement by just giving an example. All this is to say that our job here is to say whether or not this relation is reflexive. Well, we're going to claim that it's not reflexive, and the way that we do that is by giving an example. So 3 is not related to itself. So we say that 3 less than 3 is false. Is the relation symmetric? Well, remember that the definition of symmetric is this. For all elements A and B, if A is related to B, then B is related to A. To say that a relation is not symmetric means this. There exist elements A and B such that A is related to B and B is not related to A. So there exists elements that have that property. Well, let's go back up and look at our graph of the less than relation. There's the graph of the less than relation. We can see here's a pair of numbers, 2 and 5, such that 2 is related to 5, but 5 is not related to 2. 2 is less than 5, but 5 is not less than 2. So that's an example of a pair of elements that we can use to prove that the relation is not symmetric. So again, to prove that a relation is not symmetric, we have to prove this existential statement, and you prove an existential statement by giving an example. So we write this. So you give an example of two numbers, 2 and 5, such that 2 is related to 5 and 5 is not related to 2. Now what about the third property, transitivity? Transitivity is this. For all A, B, and C in the set S, if A is related to B and B is related to C, then A is related to C. Now that's a universal statement. The negation of transitivity is this existential statement down here. Now let's go back up and look at our less than relation. The less than relation is this. X is less than Y. Well, that relation is transitive. Now we have to prove that, but we can't prove it by examples because the statement of transitivity is a universal statement. The statement of transitivity is this statement, which is universal. So we can't prove that by just giving an example. We can't say, well, 2 is less than 5 and 5 is less than 7, so 2 is less than 7. That's an example. We cannot prove a universal statement by just giving an example. So how are we going to prove this? Well, the fact that this is transitive is actually just a property of real number inequality. So the transitive property of real number inequality is stated in this way. It's a universal conditional statement. It's actually the statement that we need to prove. So you can see that to prove that relations do not have a property is easy. You just give an example. You have to give an example. That example using the number x equals 3 was all we needed to be able to prove that the relation was not reflexive. This example using x equals 2 and y equals 5 was all we needed to do to prove that the relation was not symmetric. But to prove that the relation is transitive, we had to prove this universal statement. And we didn't actually have to prove it. We could just cite it, say that that's a property of real numbers, property of real number inequality. Let's go on. Example 4. Let's revisit the less than or equal to relation. X is less than or equal to y. Is this reflexive? Is this symmetric? Is this transitive? Well, let's go back up and look at the graph. There's the graph of the less than or equal to relation. Notice the significant feature of this graph compared to the less than relation graph is that the diagonal is part of this graph. So in other words, this relation is reflexive. Now how can we justify that? We have to justify our answer. Now we can't justify that by giving an example. We can't say, for instance, that 3 is less than or equal to 3 is true, because that's just an example. The statement of reflexivity is a universal statement. If you want to prove that a relation is reflexive, you have to prove this universal statement, and you cannot prove that by giving an example. So how do we prove it? Well, we just have to introduce a generic real number. So we introduce a generic real number, and we point out that x less than or equal to x is true. So x is related to itself. So saying that x can be any real number, that's introducing what's called a generic element. A generic element of the real numbers. Now, is this relation symmetric? Well, no, we can just simply give an example to prove that this relation is not symmetric. So that's the same example that we used for the previous relation, the less than relation. We proved that it was not symmetric the same way. Now this relation is transitive, and it's going to be transitive for the same reason that the less than relation was transitive in the previous example. All of this stuff actually can be used again. So in fact, I'm going to copy all this stuff and move it down to the page below, and you'll find it when we scroll back down there. So there I've copied all that stuff from the previous example, and now I just simply have to change my less than symbols to less than or equal to. So the relation is transitive. Let's go on. What about the relation from example 5? This relation, x squared equals y squared. Which properties does this relation have? Well, is it reflexive? Notice that the graph of this relation contains the main diagonal. So the points on that diagonal are of the form x comma x. So when you see that in the graph of a relation, that the main diagonal is completely contained in the relation, then that tells you that the relation is reflexive. But how do we do an official proof of this? Well, we have to introduce a generic element of the real numbers. So there's the proof. We start by introducing a generic particular element of the real numbers. So we say let x be any real number, and we somehow show that x is related to itself. So again, the statement that the relation is reflexive is a universal statement. You can't prove it by just saying, 3 is related to itself, so good, we're done. We're not done. You can't prove a universal statement by giving an example. You have to do a general proof, introduce a generic element of the set. Is this statement reflexive? Well, let's go back up and look at the graph. Notice that on this graph, every element that appears on one side of the main diagonal has a mirror image that also appears on the other side of the main diagonal. Well, that is a sign, the fact that this graph is symmetric across this diagonal is a sign that the relation is symmetric. Now, let's go back though and let's look at the definition of symmetrical relation. Here's the definition of a symmetrical relation for all pairs of elements, A and B. If A is related to B, then B is related to A. Well, we want to prove that our relation is symmetric. We want to prove that it has this property. So how do we do that? We have to do a general proof. So how do we prove that? Well, let's go back up again and look at the definition of symmetric. Symmetric is defined this way. For all A and B in set S, if A is related to B, then B is related to A. So we will prove this using a direct proof. Remember what goes into a direct proof. In statement 1, you introduce generic elements that satisfy the hypothesis. And then that's in the first step. In the final step of the proof, you prove that those elements also satisfy the conclusion. So in step 1, we say, suppose x and y are real numbers such that x is related to y. So again, we have introduced generic elements of the real numbers that satisfy the hypothesis. Now, where do we have to go with this? We have to show that y is also related to x. So that's the conclusion. So here's the gap that we need to fill. How do we do that? Well, notice that this expression is a defined term. So we have to unpack that definition. I'm going to move this line down a bit. And I'm going to be clear that that line is numbered asterisk. So let's unpack the definition of what it means to say that x is related to y. That's going to have to be statement 2. So we, by statement 1 and the definition of the relation. So we now have narrowed our gap. We don't have as much to do now. But wait a second, let's look ahead at the end of this proof. Our goal is to get to there. That's a defined expression. To say that y is related to x is a defined expression. So we have no choice about what's going to have to precede this. We're going to have a statement that says y squared is equal to x squared with some justification. And then our justification for the final statement will be by the previous statement and the definition of the relation. So in going from statement 1 to 2, we unpacked the definition of the relation, and in going from statement double asterisk to statement asterisk, we're packing the definition back up. So we've narrowed our gap in our proof. Now we just have to get from statement 2 to statement double asterisk. So that's the frame of our proof. We have no choice about that. Now we just have to figure out how we're going to make this leap. Well, wait a second. That's easy. If this is true, then we can say that this is true by the symmetric property of real number equality. So that's going to be the justification that goes there. We didn't know how this statement was going to be justified, but we knew it had to be there. So we put the statement there. But now that it's there, we can see how it's got to be justified. It's the symmetric property of real number equality that lets us interchange the order of the terms around beside that equal sign. And that's the end of our proof that the relation is symmetric. So what's interesting is that the proof that our relation is symmetric depended on the fact that real number equality is symmetric. Now let's go back up to our proof of reflexivity. Why did we know that this was true? Why did we know that x squared equals x squared is true? Well, we used the reflexive property of real number equality in that step. So the fact that our relation is reflexive came from the fact that real number equality is reflexive. But we had to show the details, show how that fact comes up. Our remaining step is to decide whether this relation is transitive or not and prove it. Well, this relation is transitive. I'll prove it on the next page. Now I want to do the proof because, again, I want to make it clear how you justify these things, how you prove these statements. Let's go back up and look at the statement of transitivity. Here's the statement of transitivity. This big universal conditional statement. It has a quantifier for all A, B, C in set S. Then it has a hypothesis. If A is related to B and B is related to C, then A is related to C. So we prove this using a direct proof. So we have no choice about how to prove that our relation is transitive. We have no choice about how to structure the proof. So we have to start with statement 1, where we introduce generic elements that satisfy the hypothesis. That's how our proof has to begin. Now remember how our proof has to end. We don't know the number of the statement, but we know that it's going to have to look like this. So this is a direct proof structure. Now where do we go from here? We've got this big gap to fill. Well, wait a second. Notice that statement 1 contains some defined expressions. X is related to Y. That's a defined expression. We have to unpack that definition. Also, this expression. Y is related to Z. That's a defined expression. We have to unpack that definition as well. So we have no choice about what's going to have to go in statement 2 and statement 3. So those two statements are just simply unpacking those red and green defined statements. So we unpacked that and wrote that. We unpacked this and wrote that. We have no choice about that. Furthermore, look where we are going to try to get to. We're trying to get to this. That's a defined expression. So we have no choice about what is going to have to go before that. We're going to have this statement here in order to get to this statement. Well, now that's the idea of packing up the definition. So we don't know how we're going to justify that statement, double asterisk, but we know now how this statement is going to be justified. This final statement is going to be by the previous statement and the definition of the relation. So look at that. Just by considering proof structure, we've got this really good frame of a proof. We just have to figure out how to bridge this gap. Well, wait a second. Look, we know that x squared is equal to y squared. We know that y squared is equal to z squared, and we're hoping to prove that x squared is equal to z squared. Well, that's easy. All we have to do is use the transitive property of real number equality. So look, we've actually closed that gap. So in fact, just considering the proof structure was all that we had to do. There were no mysterious steps that we needed to fill in. All of our statements, there are just 5 of them, were inevitable. Just by considering proof structure, we knew that those statements had to be there. So that's a great example. In fact, all 3 of these proofs, the proof that the relation was symmetric, we had no choice about how this proof unfolded. Notice we can number those statements as well. Statement 3, statement 4. All 4 of those statements had to be there just by considering proof structure. Now consider the proof of the fact that the relation was reflexive. Had 3 statements. All 3 of those statements had to be there. We had no choice about that. That's the end of that example. Let's go on. Let's recall the relation from example 6. Which properties does this relation have? Now remember that this relation had a graph that's a circle. Is this relation reflexive? Well, the key to this is to notice that the diagonal is not entirely contained in the graph. Now we can see from that graph that the relation is clearly not reflexive because that diagonal is not entirely contained in the graph. But we can't justify our answer by saying it that way. We have to justify it by, well, let's go back up and look again at the definition of reflexive. Remember, the statement that a relation is reflexive is this universal statement. The statement that a relation is not reflexive is this existential statement. So to prove an existential statement, to prove that there exists something that has some property, you have to just give an example. So let's just say this. The relation is not reflexive. And let's give an example. We have to give an example. Let's let x be 1. So then x squared plus x squared is 2. That's not equal to 1. So x is not related to itself. So we had to give an example, an actual real number that's not related to itself. On the other hand, this relation is symmetric. Notice that the graph is symmetric across this main diagonal. So that is our clue that the relation is symmetric, but we can't prove it by just saying that the graph is symmetric looking, or we can't say, 1 is related to 0 and 0 is related to 1, so there we're done. We're not done. You can't prove a relation has a property by giving an example. We have to do a general proof. So remember how that's going to have to look. The statement that a relation is symmetric is this statement. For all A and B in set S, if A is related to B, then B is related to A. So that's a universal conditional statement. We prove that using a direct proof. So the proof is going to be the direct proof format. So the proof has to begin with introducing generic elements that satisfy the hypothesis. And remember how the proof has to end. We don't know the statement number, but we know what the statement has to say. So there's our frame of a direct proof. Now, how do we fill in this gap? Well, we've done this a few times now. Notice that we have a defined expression there that we know is true. We have no choice about what to do next. Statement 2 has to be the unpacking of that statement. So we're unpacking this abbreviated statement into this less abbreviated form. And we used the definition of the relation. We unpacked that definition. Now look ahead to the end of the proof. The end of the proof has that statement. That's a defined expression. So the only way to prove this is to have previously proven what that actually means. So that means we have to precede this statement asterisk with an earlier statement that is of this form. Now, we don't know how this statement that we've squeezed in is going to be justified, but we do know now how the final statement of the proof is going to be justified. So this is going to be by the previous statement. I should number this correctly. So there's our frame. We just have this red gap to jump. How can we get from here to here? Oh, well, we don't actually have to add any statements. We can just, there's actually no gap. All we need to do is put some good justification here for going from that statement in statement 2 to the double asterisk statement. What is that justification? Well, it's the commutative property of real number addition. Notice that in statement 2, they have the x squared plus y squared. In statement 3, we have y squared plus x squared. So this is by 2 and the commutative property of real number addition. So notice that we didn't actually have to fill in any mysterious steps. All of the steps in this proof were inevitable. Finally, the question is this relation transitive? Well, this relation is not transitive. Now, how do we prove that? Remember that the statement of transitivity is this universal statement, but the statement that a relation is not transitive is this existential statement. So if we want to prove that a relation is not transitive, you just have to give examples of 3 elements, A, B, C, that have the right property. A is related to B is related to C, and A is not related to C. So here we need an example. So let's let x equal 1, y equals 0, and z equals 1. Then observe that x squared plus y squared equals 1, and y squared plus z squared equals 1, but x squared plus z squared is not equal to 1. So the proof that the relation is not transitive has to be an example. That's the end of that example. Now a new example, example 7. define a relation on this set of integers as follows. We say that the relation consists of ordered pairs m comma n that have this property. M minus n is a multiple of 5. So the question is, what properties does this relation have? Is it reflexive? Well, this relation is reflexive. Now, how do we prove that? Well, we have to prove this with a general proof. We have to introduce a generic element of this set of integers and show that it is related to itself. So we introduce an integer. Now we have to somehow get to this. So that is, m is related to itself. Now, look, that's a defined expression. To say that m is related to itself means, well, we have to precede this with this statement. We don't know how we're going to justify it, but we have to prove that this is true in order to say that m is related to itself. And so the justification for this last statement is going to be by the second to the last statement and the definition of the relation. Well, how do we prove that m minus m is a multiple of 5? Well, that's a defined expression as well. So we have to precede this statement. So, we currently have this gap in our proof, but we know that this statement has to be preceded by an earlier statement. And that statement is going to be this. So that triple asterisk statement has to be there. So now we know what the justification for the double asterisk statement will be. It will be by triple asterisk statement and definition of a multiple. Now here I've made kind of a mess of things. Everything's really crowded. So I'm going to spread stuff out. So there's our proof structure. We have the frame of a direct proof, and then we have two additional steps that we had to put in because we knew that we were going to have to, in the end of the proof, pack up the definitions. So in going from this statement to this statement, we're packing up the definition of what it means to be a multiple. And in going from this statement to this statement, we're packing up the definition of what it means to be related. So the question is how to get from here to here. Well, we can put in this statement. So notice that m minus m is just 0, and that can be written as 5 times 0, and that 0 is an integer. So we need to get to this statement where we have this k, so we need to introduce our k. So we've introduced this integer k, and that's it. The statement with 3 asterisks can actually be statement 3, and it's justified by statement 2. The statement with 2 asterisks is now statement 4, and it's justified by statement 3 and the definition of being a multiple. The statement with 1 asterisk gets numbered statement 5, and it's justified by statement 4 and the definition of the relation. So the only thing that we had to do, our only leap that was clever, was that red circled statement. All the other statements were part of the frame that we get from just considering the proof structure. So we're going to do a similar thing in proving that the relation is symmetric. I'll do that on the next page. Well, to prove that the relation is symmetric, let's remember what the proof will entail. Here's the statement of symmetry. For all A and B in set S, if A is related to B, then B is related to A. We'll build a direct proof, so in statement 1 of the direct proof, we'll introduce A and B that have that property that A is related to B. That'll be in step 1. In the final statement of the proof, we'll have this. So we say, suppose A and B are integers such that A is related to B. So those are generic elements that satisfy the hypothesis. And then we know how the proof has to end. It has to end by saying, therefore, B is related to A. All right, well, what next? We've got this big gap to fill. But wait a second. There is a defined expression. So let's write down what that really means. Let's unpack that defined term. So A minus B is a multiple of 5. Hey, that's also a defined expression. To say that A minus B is a multiple of 5 is a defined expression. We have no choice about what has to come next. So statement 3 is unpacking that defined expression. So the justification for statement 3 is by 2, and the definition of is a multiple of. All right, so the gap in our proof has gotten narrower. Oh, but hey, look at the end. The end of the proof has a defined expression in it. So there is no choice about how we have to get there. We have to get there by previously, in the step just before, we have to have proven this. So that's going to have to be justified somehow. We're going to have to prove that B minus A is a multiple of 5. So there's got to be some justification here. But we know now how the last statement is going to have to be justified. The last statement is going to have to be justified by the previous statement and the definition of the relation. But wait a minute, that is also a defined expression. So we know what's going to have to precede this statement. Now we don't know how that's going to be justified, but we're going to have this statement. There exists an integer j such that b minus a equals 5j. And then we pack that up into this more concise statement. We say that b minus a is a multiple of 5. So this will be justified by statement 3 asterisk and the definition of multiple. So we know that the proof has to start with unpacking this defined expression to give us this, and then unpacking that defined expression to give us this. And we know that at the end of the proof, we're going to have to get to here somehow, and then pack up that into this more abbreviated form using the definition, and then pack that up into this more abbreviated form using another definition. So this gap is what we're facing. Well, notice a couple of things. I used a different letter J in step triple asterisk than the letter that I used in step 3. Step 3, I used the letter K, so in step triple asterisk, I couldn't use K, I had to use a different letter J. Now we know that this integer K exists because we've gotten to statement 3 using stuff that we know is true. But we have to come up with this integer j that's going to make this true. So how can we get to the fact that this is true, and how can we find a j that will work? Well, here is where we have to be clever. We have to conjure up something that will work here. One thing is to notice that we have an equation here that's a minus b equals 5k. We want to build an equation that's b minus a equals 5j. Let's start by just building the left side of this equation. go back up, make this statement 4. So statement 4, we just use statement 3. We point out that b minus a is minus 5k. Well, look, we've got now an equation that says b minus a equals minus 5k, and we want to have an equation that says b minus a equals 5j. So let's keep going. So now we have an equation that says b minus a equals 5 times minus k, and we want to have an equation that says b minus a equals 5 times j. So let's just introduce j at this point. We're going to say that j equals minus k. We have to point out that j is an integer. So look, we have closed our gap. We can now number statement triple asterisk S statement 6, and it's justified by statement 5. And we can renumber statement double asterisk as statement 7, and it's justified by statement 6 in the definition of multiple. And finally, the last statement of the proof is going to be numbered statement 8, and it's justified by statement 7 in the definition of the relation. So the only clever thing that we had to do was that red circled pair of steps in the middle. All the other steps in this were straightforward. So there's the proof that the relation is symmetric. Now the relation is also transitive. Now how do we prove that? Well, we have to set up a direct proof. We know how this proof will start. And we know how this proof has to end. Now, at this point, I'm going to stop talking and just write the steps. And you can see from the order in which they get written down, you can see the logical progression of my thoughts. So there is the frame of our proof. The outer frame is the frame of a direct proof, and then we have a couple of layers of unpacking and packing up definitions. We have no choice but to unpack that definition to this. We have no choice but to unpack that defined expression and write this in its place. And we have no choice but to unpack that defined expression and write this in its place. And we have no choice but to unpack that defined expression and write this in its place. And then looking ahead to the end of the proof, we know that the only way to get to this statement is to have previously proven this. And the only way to get to this statement is to have previously proven this. So those are a bunch of steps. 8 steps that are just simply obtained using proof structure thinking. Also, notice that I came up with different letters for my integers. K was chosen already, so I had to use a J or something else there. J and K were both used up, so I had to use something else. Here, I used an H. Now we have to bridge this gap. Well, look what we're trying to get. We're trying to get to this equation that says A minus C equals 5H. We don't know what H is. We don't know what A and C are, but we can start by writing down A minus C and see if we can get somewhere from that. So let's go back and create a step 4. Now here I'm going to do a trick. I'm going to write A minus C. That's what I want to have on my left side of my equation. I'm going to write it in this tricky way. I'm going to write A minus B plus B minus C. That is a trick. But now look, we know what A minus B is. A minus B is 5K. We know what B minus C is. B minus C is 5J. Now look where we're trying to get. We're trying to get to this. We want A minus C to equal 5H. So let's keep rewriting. Now look how close we are. We want to get to a point where we say that A minus C is 5H. What we've got so far is A minus C is 5 times this stuff. Oh, well that gives us an idea for introducing a letter H. So we introduce our letter H, and we observe that A minus C equals 5H, which is where we wanted to get to. So we've filled our gap. So these steps, these 2 red steps, 6 and 7, were the only tricky thing that we had to do in this proof. Everything else, all these other 8 steps, were inevitable. They're part of the frame that had to be there by considering proof structure. So we can number our steps now. And there's our proof that the relation is transitive. Let's go on. Now I want to talk about what are called equivalence relations. An equivalence relation is a relation on a set S that is reflexive and symmetric and transitive. So for example, let's go back up and look at our examples 4, 5, 6, and 7 and figure out which of these are equivalence relations. So actually we should visit all of our examples. So example 3 was not reflexive and is not symmetric. It is transitive though, that was good. But relation 3 is not an equivalence relation because it's not reflexive and not symmetric. Let's look at relation 4, the less than or equal to relation. It is reflexive, that's good. It is transitive, but it's not symmetric. So relation 4 fails to be an equivalence relation. Let's go back and look at relation 5. Relation 5 was this relation. To say x is related to y means that x squared equals y squared. Notice that that relation was reflexive, it was symmetric, and it was transitive. So relation 5 is an equivalence relation. Let's go back up and look at 6. Relation 6 was the circle relation. That relation was not reflexive and was not transitive. It was symmetric, that was cool, but it's not qualified to be called an equivalence relation. And then finally, relation 7. This relation involving the difference of integers being a multiple of 5. Notice that that relation was reflexive. That relation was symmetric, and that relation was transitive. So relation 7 is an equivalence relation. The last thing that I want to talk about is what are called equivalence classes. We have this symbol, square brackets with a little s inside. That symbol gets used in this situation. There is some equivalence relation called capital R, maybe, on some set capital S in the discussion already. And little s is an element of capital S. And this symbol is spoken the equivalence class of little s. What it means, what that symbol means, is the following. That symbol stands for the subset of S that consists of all of the elements of capital S that are related to little s. So that is, this symbol, the equivalence class of little s, is all of the x's in set capital S, such that x is related to little s. And some additional terminology, that element, little s, is called a representative of the equivalence class, bracket S. So for example, go back to the relation from example 5. It was this relation. To say that x is related to y means that x squared equals y squared. What's the equivalence class of 2? Well, that's the set of all real numbers that are related to 2. It's going to be that set containing 2 real numbers. Negative 2 is related to 2 because negative 2 squared equals 2 squared. And 2 is related to 2 because 2 squared equals 2 squared. What's the equivalence class of 5? Well, that's going to be easy. What's the equivalence class of negative 2? Oh, we've already written that one down. It's that one again. What would be a general description of all the equivalence classes? Well, there are sets of this form. So any set of this form is an equivalence class. What is the equivalence class of 0? Well, that's going to be, well, it's just going to be the set 0. Does that agree with the answer from D? Well, yeah, because this set is actually just 0. So in set terminology, set notation, you write this. You don't allow repeated elements. So this symbol is kind of cheesy. I kind of made this up, but it's okay. You get the idea that for most elements of the real numbers, the equivalence class is going to be a 2-element set, and for this one element of the real numbers, the equivalence class is going to be just a single element set. Let's go to example 7. Remember, the relation in example 7 was this. The relation was m is related to n means that m minus n is a multiple of 5. So what's the equivalence class for the number 2? Well, the number 2 is certainly in there because 2 minus 2 is 0. That's a multiple of 5. The number 7 is in there because 7 minus 2 is 5. That's a multiple of 5. The number 12 is in there because 12 minus 2 is 10. That's a multiple of 5. And so on. You can just keep going. But we can go the other direction as well. Minus 3 is in there because minus 3 minus 2 is minus 5. That's a multiple of 5. And the number minus 8 is in there because minus 8 minus 2 is minus 10. That's a multiple of 5. So the equivalence class of the number 2 is this big set that goes on forever in both directions. What's the equivalence class of the number 4? Well, it's going to look like this. This infinite set of integers. What's the equivalence class of negative 3? Well, that's the same set we wrote down earlier. Question D. What would be a general description of all equivalence classes? Well, the equivalence classes could be described this way. Notice that there are 4 equivalence classes. One is this one that's made up of the number 2 and all the numbers that are related to 2. We've seen that up here. So there's the number 2 and all these other numbers that are of the form 2 plus 5k, where k is some integer. Then there's this equivalence class, this green one, consisting of the number 4 and a bunch of other numbers that are 4 plus some multiple of 5. So each of those numbers fits this description, 4 plus 5k, where k is an integer, and so on. So we get a total of 5 different equivalence classes by using 5 different seeds, representatives, that will give us these classes. The last thing I want to talk about, I'm not going to prove, but I will talk about this theorem about equivalence classes. This theorem says if you have an equivalence relation on a set S and you choose any 2 elements of the set S, well then either the equivalence classes are completely disjoint or their equivalence classes are exactly the same set. Now this should be believable. Let's go back up and look at our example that we just did. Notice the equivalence class for 2 was exactly the same as the equivalence class for 3. Every element of those 2 sets was the same. Whereas the equivalence class for 4 didn't have any elements in common with the equivalence class for 2. Let's look at the previous example. Look, the equivalence class for 2 was the same as the equivalence class for -2. The equivalence class for 5 was completely disjoint from that. So this theorem about equivalence classes is believable. 2 equivalence classes for a relation are either exactly the same set or they're completely disjoint. So that is, there's no partial overlap of equivalence classes. This also tells us that it doesn't matter which element of an equivalence class we use as a representative of the class when we write down the symbol for that equivalence class. So for example, in the previous example, this symbol denotes this class, this symbol denotes this class. In this symbol, 2 is being used as the representative of that class, and in this symbol, the -3 is the representative of that same class. So it doesn't matter which element of an equivalence class we use as a representative of the equivalence class when we write the symbol for that class. Put another way, we can say this: there can be many representatives of a particular equivalence class. Remember, when I defined equivalence classes, I said the element S is called a representative of the equivalence class. I didn't say the representative, I just said a representative. There can be many representatives. That's the end of our discussion of equivalence classes. That's the end of the video. Thank you.